Hello friends, we are here with discussion of Bode plots, which is part of our unit 6. In continuation with the discussions we had regarding mathematical modeling of physical systems, as we recollect, we built up the mathematical equations of operations of various mechanical systems. We took some examples of spring mass dashpot systems wherein we got certain differential equation of second order which described the behavior of mechanical system. In particular, we discussed about spring mass dashpot system, which was modeled from the suspension system of an automobile. Now one would ask a question, sir, after building this mathematical equation of operation, what is the use of these equations those we have derived? So the answer is very simple, friends. These equations of operations are converted into input-output relationships called as transfer functions of those systems. Now, these transfer functions are nothing but ratios of output parameter and input parameter. Now, in particular, if you're talking about the spring mass dashpot system, the equation of operation, if you remember, was F, external force applied F, was equal to mx double dot plus bx dot plus kx. Or in other words, the external force F was equal to m d square x plus b dx plus kx. Or in the operator form, the equation was external force F is equal to m d2x by dt squared plus b dx by dt plus kx. Now this is the second order equation, differential equation. This is the second order ordinary differential equation. And it is also called as time invariant differential equation because time was not varying. Time is because all the differentiations are with respect to time. So we call it as time invariant ordinary differential equation of second order. And this is also called as a linear differential equation. Why? Because it is of first degree. First degree, what do you mean by first degree? It is the power of the highest derivative. Now in this case of spring mass dashpot system, F is equal to m into d2x by dt squared plus b dx by dt plus kx. Now in this second order differential equation, what is the highest power? 2, that is d2x by dt squared. And the exponent or power of this highest order is raised to 1. And hence this equation is called as linear differential equation. Okay. Now the solution methodologies are there, but we are interested in the transfer function. Now, when we just convert this differential equation into transfer function, if you just refer back the earlier lectures, what is this transfer function? It is the ratio of output by input. So what is the output? Output is the displacement x and the input was force F. Now I need to convert this differential equation into this transfer function format. Now, if I just convert this equation into operator form, F is equal to md square x plus bdx plus kx. If I take out x common, the equation remains as becomes F is equal to md square plus bd plus k bracket multiplied by x. Now, if I take the ratio x by F, what I get, x transfer function of this spring mass dashpot system is equal to output by input, which is equal to output is x, x upon input is f, x upon f is equal to 1 upon md squared plus bd plus k. So 1 upon md square plus bd plus k is the transfer function. Now if I convert this time domain transfer function into Laplace domain transfer function, if you just remember, I need to convert this d terms into s terms. I simply put d is equal to s, and while taking Laplace transform of this transfer function, we make a major assumption that initial conditions are put to 0. So what the transfer function becomes, transfer function is equal to earlier I was calling it as xt by ft, that being function of t. Now it will be in Laplace transform terms, it will be xs, x into bracket s. So that is x is a function of Laplacian variable s upon f of s is equal to 1 upon, instead of d I'll be putting s, 1 upon m s square plus bs plus k, isn't it? So 1 upon ms square plus bs plus k is my transfer function in Laplacian domain. Now what I do with this transfer function, as we discussed in the earlier lectures, we said we do this mathematical modeling to predict the performance of this system. Now how do I predict the performance of the system? I subject this transfer function to variety of inputs, variety of input function. Now what is the input function here? Input is force F. Now I try to simulate the real life situations, and I think what that physical system actually will be subjected to. Okay, so it is let us say it is climbing a slope, a ramp. So it is a Now this suspension system is subjected to gradually increasing force. Now I call it as a ramp function input. So what I do, this transfer function, which is the ratio of xs by fs, I put fs is equal to the input function, which is equivalent to a ramp function. What is this ramp function input? Ramp is the force is continuously varying, increasing with respect to time. If I just put it on a graph paper, if I put t on x-axis and f on y-axis, so as the time increases, force is also increasing. So I'll get a straight line, a ramp type of a sloping line. What does that mean? If I just take points on that line corresponding to point 1, at time 10 seconds, the force was 10 Newton. After 10 more seconds, the force has become 20 Newton. So proportionately with respect to time, the force is gradually increasing. The same thing happens when your vehicle or a motorcycle is climbing a slope. So that is the physical situation. Mathematically, what I do, I subject my transfer function to a ramp input, which simulates a sloping physical condition. And what I do, I put fs is equal to ramp input. I put the mathematical equivalent of that ramp input. Maybe in this case, it will be a into t. A is the slope, t is the time. And I then try to find out what will be xs. Displacement x, isn't it? For a linearly increasing force function, how is the displacement varying? As I solve this differential equation, I solve this transfer function. And then whatever is the displacement I'll be getting, I try to find out whether it is within the permissible limit or not. If it is not, what I do, I keep on changing. On the right hand side of my transfer function, what is there? 1 upon m d square plus bd plus k. Now what are the variables? Mass can be varied, damping factor b can be varied, k can be varied. Now this I'm doing it virtually, I'm doing it on paper. I'm just changing the number. M was having some numerical value, maybe 100 Newton. I changed it to 150 Newton. B was having some value 5. I changed it to 7. K was having some value 15. I change it to 10, maybe. And I try to find out what will be the X value, right? Or in other words, I'll be solving this differential equation of operation for this ramp input, and I'll be getting the corresponding output. Getting the output in the sense, I'll be, whatever is the solution, this solution will be in terms of X. That is the displacement transmitted by this spring mass dashport system. Now I just continue varying the input parameters, varying the system parameters, which are M, B, and K, till I get the displacement transmitted within the reasonable limits. Now this is how the time response analysis is carried out. Now, while predicting the performance of the system, we make use of two approaches. First, I provide the time-based functions, that is called as the time response. I provide step input, I provide impulse input, I provide ramp input, I provide sinusoidal input. I give these time-based input functions, and then I solve the differential equation for these variety of inputs, and whatever outputs I get, if those are not within my desirable limits, I just go on iterations or iterating the values or changing the values of M, B, and K till I get my desired value of output. Now this is how the mathematical analysis is done and the system performance is predicted. And this can be done for all the physical systems, provided I have a nicely built mathematical equation of operation based on sound physical principles and most relevant physical principles. Then whatever predictions I make, those will be most useful for the designer, isn't it? So these are the time response characteristics briefly I discussed. Similarly, another way of predicting the system behavior is by subjecting this transfer function, by subjecting this differential equation of operation to frequency-based functions or frequency response. That is also called as frequency response. When I use impulse, step, ramp functions as the input, I call it as, and I predict the behavior. Time-based prediction of the behavior is called as time response. And the second category is frequency-based predictions are called as frequency response. Now that also provides me very good information about system behavior. It also tells me about the stability aspect of the system. To what input values the system behaves in a stable manner. For what values of system parameters the system tends to become unstable. And at what cutoff value of the system parameters the system becomes totally unstable. The system goes out of control. So these are predicted by using frequency response methods also. Now there are a number of methods of frequency response analysis. There are many scientists have worked out on the mathematical tools for predicting the system performance by using frequency response method. Now those are called as polar plot approach is there, logarithmic plot approach is there, Bode plot approach is there, and even root locus techniques are used. There are Nyquist approaches used for predicting the system behavior. Now, in particular, we'll be focusing as relevant as it is relevant to our curriculum. We'll be discussing one of the frequency response methods that is called as Bode plots. This is a graphical method. Yes, we plot the graph for different values of inputs, and then by analyzing the graphs, we can predict for what values of system parameters the system is stable, for what values of system parameters the system tends to become unstable. So Bode is the name of the a scientist or mathematician who devised this technique, hence those are called as Bode plots. Now, what is this Bode plot? The frequency response of a system is the set of the values of the magnitude g of j omega and phase angle phi that occur when a sinusoidal input signal is varied over a range of frequencies. Now, as I said earlier, to my transfer function, I provide frequency input. A frequency input, maybe a sinusoidal input I give. In case in that taking the same case of my spring mass dashboard system, the force will be a frequency function or a sinusoidal function, let us say. So F will be F sine of omega t will be the input function, isn't it? That the force is varying harmonically. The force is varying sinusoidally. So that is my input function. Now to this sinusoidal input signal, how the system behaves. The study of this system behavior is depicted by using a Bode plot. Now, the Bode plot has got two parts, or two graphs we draw. Magnitude of G. What is this G? G is the transfer function of a system. Now, G of S. As I discussed earlier, a Laplace transform of my transfer function. It is G of S. While solving the block diagram problems also, we used GS into HS, if you remember. So what G of S means? This transfer function G is a function of Laplacian variable S. Now, if this transfer function is a function of time t, what I'll be calling it as? G of t, time t. So G of S is the transfer function. Now, when I carry out frequency response, when I give a sinusoidal input, normally practice is that sinusoidal function is given in the form of complex variable, isn't it? If you remember, this sinusoidal input can also be given, can also be represented by putting S is equal to j omega. Omega is the angular frequency, isn't it? Same as your sine of omega t, that omega is angular frequency, isn't it? Or angular velocity we call it as. So that is the angular frequency. Now this sinusoidal input is mathematically represented by putting S is equal to 0. So earlier my function was G of S. What I am doing now, I put S is equal to j omega. So it becomes G of j omega. And what are these signs? Two lines. These are called as mod of Gj omega. Mod of Gj omega. So what is this mod of Gj omega? Let us say S is represented by some sinusoidal function 1 plus j omega, right? Which corresponds to some sinusoidal input. Now when I take mod or magnitude of that G of S, what it becomes? How do you find out the magnitude? Magnitude is square of real part plus square of imaginary part. Now in this input 1 plus j omega, j is a complex number. So 1 is the real part and omega is the imaginary part. So square root of real part square plus imaginary part square. So square root of 1 square plus omega square. The square root of 1 plus omega square is the mod of or magnitude of that transfer function in frequency domain, right? Versus this angular frequency omega. For different values of omega, what are the magnitudes of my transfer functions corresponding to the sinusoidal input? So this is one graph or one plot I get. So on x-axis I have got omega, angular frequency, and on y-axis I have got magnitude. And second graph is phase angle phi in degrees plotted against, once again, omega, angular frequency omega. So this phase angle plot provides me about the information, phasor information. whether there is phase lag or phase lead. When I provide a frequency input function, what happens to the magnitude of the output and what happens to the phase angle of the output function. So these two plots together are called as Bode plot. The magnitude and angular frequency are plotted using logarithmic scales. So normally these are plotted by using a semi-log paper. We'll discuss about it later. So omega is plotted on x-axis as I said, but the scale is not linear. The scale is logarithmic. Now this logarithmic scale, there are benefits of logarithmic scale. What are the benefits of taking logarithms? Anyone? The multiplications become summations, the divisions becomes subtraction, plus the squares, cubes, all these things become multiplications once again. And what else? I can convert a large number into a small number. So if I got frequency scale from 1 to 10,000, if I use a regular scale, that is decimal scale, I require a very long, big graph paper to accommodate various values from frequency 1 to 10,000. Now, if I just convert it into logarithmic scale, what happens? So log of 10,000 will be, what is 10,000? 1 into 10, 20, 30, 40. So what becomes, log of 10,000 becomes 4 point something, 4.000. So what has happened? The scaling down has happened. The number 10,000 is converted into 4, a single digit number. So I can just scale down by using logarithmic scale, isn't it? So that is one more benefit of using logarithmic scale, isn't it? So x-axis, the frequencies are normally converted into logarithmic scale. So the x scale is logarithmic scale, but y scale is regular decimal scale. Where I plot y scale, in the first graph I plot magnitude, which is normally in decibel. We'll discuss about that later. So magnitude, which is on a regular decimal scale, even the phase angle, just beneath that magnitude versus omega plot, I draw the phase angle versus omega plot. So on this semi-log paper, why I call it a semi-log paper? Semi, half. So one axis, x-axis has a logarithmic scale. So the gradations on that graph paper, on the semi-log paper, are on the logarithmic scale on the x-axis. Whereas on the y-axis, I have got, I'll show you a piece of paper. On the y-axis, I have got regular decimal scale. So on y-axis, I plot magnitude. And in the second graph, on the y-axis, I plot phase angle in degrees. So both these plots together constitute this pair of graphs is referred to as a Bode plot. So magnitude is expressed in decibel units. Now, what is this decibel units? If you are attentive enough while studying the subject of measurements or instrumentation, we must have studied about sound measurement, acoustic measurement. For sound measurements, we use this decibel scale, decibel, bell. Decimal of that bell is decibel, right? So decibel. So decibel, what is this decibel? Decibel is 20 log to the base 10 of a given parameter. If you remember in sound or acoustic measurement, 20 log to the base 10, 20 log to the base 10 of P2 by P1. What was it? P2 was the unknown sound pressure level and P1 was the reference sound pressure level, isn't it? And 20 log to the base 10 of that P2 by P1 was called as decibel magnitude. Apan manat nahi ka, our hearing is, or sound pollution is measured in decibel, on decibel scale. 50 decibel cha puda it becomes painful, or at 150 it is 150 decibel, it becomes harmful to your ears. If you have read the newspapers and scientific articles, based on decibel scale. So particularly on for sound measurement, the decibel scale is invariably used, but it can be used for any of the parametric conversion. So as I said, decibel, 1 decibel is 20 log to the base 10 of that parameter. Now in this case, we are having the parameter or a transfer function mod of gj omega in decibel will be 20 log to the base 10 of mod of gj omega. So whatever transfer function I have got, I try to take the magnitude of that, and that I take a log of that magnitude and multiply it by 20. It gives me my decibel scale of magnitude. And similarly, phase angle. How to get a phase angle in degrees? So phase angle of gj omega in degrees is equal to, please be attentive, phase angle of gj omega in degrees is equal to tan inverse of ratio of imaginary part upon real part. Now if we have the term 1 plus j omega is a complex number, s is equal to 1 plus j omega, right? So what is the real part? 1 is the real part and omega is the imaginary part. So what will be the phase angle of this 1 plus j omega? It will be phase angle of 1 plus j omega will be equal in degrees will be equal to tan inverse of ratio of imaginary part upon real part. Now what is the imaginary part of 1 plus j omega? Omega is the imaginary part and 1 is the real part, isn't it? So tan inverse of omega upon 1. So tan inverse of omega, whatever is the angular frequency, if I just take the tan inverse of that, it will give me phase angle in degrees. Now this is how, from my transfer function value, I need to find out the magnitude in decibel, I need to find out phase angle in degrees, and then I need to plot two graphs, one magnitude versus omega or log of omega, let us say, and second graph phase angle in degrees versus log of omega or omega on x-axis. So these two plots together are called as Bode plots. Now from the nature of the plots, how the variations are taking place for each of the terms of my transfer function, I find out what are some stability terms called as the gain margin and phase margin. So these gain margins and phase margins should be positive for the system to be stable. If those are not positive, the system tends to become unstable. Now, as a designer, because I'm working on paper, I'm working on mathematical terms, what I can do, if for given values of the transfer function, for a sinusoidal input, if the system is tending to be unstable at particular parametric values, as a designer on paper, what I can suggest, change these values of the parameters so that system becomes stable. So this is what is the prediction of the system behavior based on Bode plots. Like that, for various frequency response methods, I can have different approaches for predicting system behaviors, right? Now in this particular case, we are going to study Bode plots to some details. Now what is the semi-log paper? I just talked to you regarding this. So on x-axis, I plot omega in radian per second, and on y-axis, in the first part, decibel magnitude. If you see the scale on y-axis, it is regular decimal scale. It is available in the market. 1 rupees, you can get this semi-log paper. Why this semi-log? I can have log paper also. So y-axis also, I have logarithmic scale, and x-axis also I got a logarithmic scale. That is called as log paper. And regular graph paper, y-axis decimal scale, x-axis also decimal scale. In semi-log paper, one of the axis is logarithmic and the other axis is decimal. Hence the name semi-log paper. So in my Bode plots, I use this semi-log paper. In this semi-log paper, one half of this semi-log paper I use for magnitude plot, magnitude versus angular frequency omega. And second half of the graph I use for phase angle versus omega on logarithmic scale. So these two plots, magnitude or plots and phase angle plots together are called as Bode plots. Now on the x-axis, what difference you can see? Here there are equal divisions, but the divisions are decreasing divisions. Now from first to this point, I have got 10 divisions. Just measure 1, 2, 3, 4, up to 10 divisions will be there. Decreasing divisions. Now this is called as one decade. This logarithmic plot terminology is called as one decade. Once again, from this line to this line, I have got 10 divisions. Another decade, third decade, fourth decade, fifth decade, right? Or these are also called as cycles. First cycle, second cycle, third cycle, fourth cycle, 5 cycles. So this is a sheet of 5 cycles. I can have a sheet of 10 cycles. I can have a sheet of 20 cycles. So this is a sheet of 5 cycle semi-log paper. This is the type of paper usually used for preparing Bode plots, right? Okay, so what I do? 0.1 to 1. I increase the values of frequency from 0.1, 0.2, 0.3, 0.4, go up to 1. Then from 1 to maybe 10. So 1, 2, 3, 4, 5, 6, up to 10. From 10 to 100. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. From 100 to 1000. 100, 200, 300, 400, 500, 600, 1000. From 1000 to 10,000. 1000, 2000, 3000, 4000, up to 10,000. So a small piece of paper, I am accommodating values of large values from 0.1 to 10,000. Had it been a regular scale, the graph would have been very clumsy, isn't it? Now by using this logarithmic scale, I am making my graph more meaningful and I am reducing the scale, right? So this is the semi-log paper. Now let us, before going into the actual plots part, friends, let us understand what are the poles and zeros of a given transfer function. What is a transfer function? We have already seen. A transfer function is defined as a ratio of the Laplace transform of the output to the Laplace transform of input with all initial conditions equal to 0. Transfer functions are defined only for linear time invariant systems. Transfer functions can usually be expressed as the ratio of two polynomials in complex variable s, right? And those polynomials can be factorized. A transfer function can be factored into following forms. So gs is equal to k into, I can have k into s into bracket. So factors can be variety of factors. Bracket, first order factors, that is, I can have k into s into first order factors s plus 1, s plus 2, s plus 3, right? Let it be attentive. K into s into bracket s plus 1, s plus 2 into s plus 3. And denominator, let us say it is factored as, once again I have got s in the denominator into bracket s plus 1, maybe s plus 5 into s plus 6 into s plus 7, right? Now the roots of the numerator polynomial are called zeros. Please be attentive. The roots of the numerator polynomial is the numerator polynomial. The roots of the numerator polynomial are called as zeros. Now why they are called as zeros? Take this case. S plus 1 was the term. Now here what is written? S plus z1. So S plus 1 is the first zero of this polynomial. S plus 2 is the second zero of this polynomial. S plus 3 is the third zero of this polynomial. So there was S into S plus 1 into S plus 2 into S plus 3. So these are called as 1, 2, 3 are called as 3 zeros of this polynomial. Why those are called as zeros? Because putting these values in place of S. So S plus 1, if I solve it, S becomes equal to minus 1, isn't it? So if I put minus 1 here, what happens? This term becomes 0. Now once this term becomes 0, 0 multiplied by anything, it makes the numerator 0 and it makes the entire ratio 0, right? So that value of the factor in the numerator for which the ratio becomes 0 is called as 0 of that system, right? Got the point? So numerator factors, whatever are the factors, numerator factors correspond to zeros of that system. And what are the denominator factors? S plus P1, S plus P2, S plus P3. So what I said, S plus 5, S plus 6, S plus 7. No, S plus 5. So S is equal to minus 5. If I put S is equal to minus 5, what happens? This term becomes 0. So when this term becomes 0, the entire denominator becomes 0. And when the denominator becomes 0, whatever be the numerator, if the denominator becomes 0, the ratio becomes infinite. So what is the conclusion? The values of the factors in the denominator which make the entire ratio infinite, which make the entire ratio infinity, are called as poles of that function. So denominator factors define the poles of the system. Numerator factors define the zeros of the system. Okay, so these are called as the first order zeros. S plus 1, S plus 2, S plus 3. If I got a factor S square plus 2S plus 1. So if I just, so S square, so this is second order. So those are called as second order factors, right? I can have real factors, I can have imaginary factors, I can have complex conjugate factors. So variety of factors can be there in my transfer function, the numerator as well as denominator. Okay, so I had said one more thing. K is called as the constant or steady state gain of this transfer function. And then I got S as one of the factors. Now what happens? So that S is also called as 0 of that function, of the transfer function. But that S, that 0 will be for the value of S is equal to 0, isn't it? So if I got a multiple S in the numerator, that becomes my 0 at the origin. And then this is the first order or simple 0. And then if I got S square plus 2S plus 1, that is called as second order 0 in the numerator. Similarly, in the denominator, if I got S into S plus 5 into S plus 6 into S plus 7. So how many poles I have got? 4 poles. Because for S is equal to 0, the entire denominator becomes 0 and the entire ratio becomes infinite. So S is equal to 0, S in the denominator at S is equal to 0 gives my first pole at origin. Second pole is the simple pole. So for that value S plus 5, for S is equal to minus 5, I got one more pole. At S is equal to minus 6, for the factor S plus 6, for S is equal to minus 6, the denominator becomes 0 and the ratio becomes infinite. So that is called as second pole. And for S is equal to minus 7, I got third pole. And at S is equal to 0, that is the pole at the origin. The poles are those values of the factors in the transfer function which make the entire transfer function infinity, are called as poles of that function. And zeros, the roots of the numerator polynomial which make the entire ratio 0, are called as zeros of that function, right? I think the things are clear. So I can have 0 at origin if I got multiple S, first order 0 or simple 0, and I can have second order 0. Similarly, I can have pole at the origin at if I got S in the denominator. So pole at the origin in the sense is for S is equal to 0, I have one pole. For S is equal to minus 5. So this is a simple pole or first order pole. If I got a quadratic factor, second order factor, S square plus 2S plus 1, whatever it is, I got second order pole also. So I can have a constant in my transfer function. I can have 0 at origin. I can have simple 0. I can have second order 0. Similarly, I can have pole at the origin. Pole at the origin. I can have simple pole. I can have quadratic pole or second order pole. Right? So these are called as poles and zeros. Now let us see how these are graphically plotted. As an example, you are given the following transfer function. Show the poles and zeros in the S plane. Now, this is my regular graph paper now. Now, the x-axis is the real axis, sigma axis is the real axis, and j omega axis is the imaginary axis. And this is called as S-plane. Because S is equal to sigma plus j omega, right? S is equal to sigma plus j omega. Sigma is the real part of S, and omega is the j omega is the imaginary part of S, right? So this is a real axis, this is the imaginary axis. This is sigma axis, this is j omega axis. Now let us see this transfer function. Please be attentive. GS is equal to S plus 8 into S plus 14 divided by S into S plus 4 into S plus 10. Now, can anyone tell me? Just please be attentive. How many zeros are there for this transfer function? Two simple zeros. For what values of S I have got zeros? If I put S is equal to minus 8, I get this term 0 and the entire ratio 0. So at S is equal to minus 8, I have got 0. Now how do I plot it? So S is equal to minus 8. Minus 8 is a negative real number. So on real axis, I put minus 8. And this 0, I plot it by using a hollow circle. Right? This is minus 8. First 0 I have plotted here. Now, second 0, at S is equal to minus 14, the numerator becomes 0 and the entire ratio becomes 0. So S is equal to minus 14 is my second 0. So S is equal to minus 14. One more hollow circle. So two zeros are plotted on negative real axis because these factors are real factors. If the factors are imaginary factors, I need to plot it on imaginary axis. If the factors are complex conjugate, I take the real part and imaginary part and I plot it accordingly. Okay. So these are the zeros. Minus 8 and minus 14 are the zeros which are plotted in the S plane. Okay. Now, denominator. S is equal to 0. Makes the denominator 0 and makes this ratio infinity. So this is the first pole. So pole S is equal to, at S is equal to 0, I got first pole. Now poles are represented by a cross line and zeros are represented by hollow circle. So pole is a cross line, right? So first pole at S is equal to 0. Now second pole is at S is equal to minus 4. Because S is equal to minus 4 makes the denominator 0 and the ratio infinity. The second pole is at S is equal to minus 4. I put a cross at minus 4. Third pole is S is equal to minus 10. S is equal to minus 10. I plot and I draw a cross. So three poles for the three factors in the denominator. First pole, second pole and third pole, and two zeros. Minus 8 and minus 14. So this is called as the pole zero plot of a given transfer function plotted in S plane. Quickly, I'll just wind up, friends. So this pole zero plot is very relevant in analysis of stability in general. Just please be attentive. If the factors of a transfer function are lying, or the roots of the transfer function lie on the left half of my imaginary axis, all the factors are lying on the left half of the imaginary axis, the system is stable. And if the factors lie on the right half of the imaginary axis, the system is called as unstable. I repeat, if the factors or the roots of this transfer function lie on the left half of S plane or left half of imaginary axis, this part, this entire part, the system is stable. And if the factors are lying on the right half of the S plane or right half of imaginary axis, the system is unstable. And if the roots are lying on the imaginary axis, the system is marginally stable or conditionally stable. For certain values of K, steady state gain, the system is tending to be stable. So what are the three types I said? The system is completely stable if the roots lie on the left half of S plane. The system is completely unstable if the roots lie on the right half of S plane. And the system is conditionally or marginally stable if the roots lie on the imaginary axis. So in general, this is the stability criteria. This is how we analyze the behavior related to stability of a given physical system just from the transfer function. Just by having a pole zero plot, I can just generally predict how the system will be stable for given values of parameters. I think we'll stop for this lecture, friends.